Blue. Isn't that the best thing to fly?
No matter how much you want I was thinking I should tell her my story about my alcohol, make her feel better. I think that would make everybody feel better.
All right, I was going to do this, but it's not. It wasn't working. See, it's for some reason Safari suddenly decided to update itself.
It was something I thought I knew, but I didn't. Well, I feel, well, you're also dating gossip girls, so that's why literally gossip girls. That's what he should.
All right, here you go.
Let's try to well, we talked about anonymous last time, so I feel like it's down. Yeah, I'm gonna take it.
Yeah, nice.
Yeah?
Yeah.
Good.
I'm doing it. Yeah.
We're getting 24. Is that it? Not supposed to be.
As in Beatrice. Yeah.
Okay, please don't leave wrappers and random stuff in the room. Okay?
Stumps.
Random stuff.
Oh.
I got 23. Make a guess. Got a 20% chance.
Well, I was walking in here and Carly and Callie coming in there like, they thought I'd go home last night.
Hey, here's
So I just
Okay, do you think that they are stereoisomers or identical compounds? What do you think? Okay, why did you say that? They're Fischer projections, and they are, remember the deals are coming out. Okay, and are they mirror images? Okay, and do you see that if you pick that up and try to put it on top of here, it wouldn't match up? Okay, so what are they? They're enantiomers. Oh, Lee, give me a pen. Okay. Okay, so draw me a diastereomer of the first one. Here's the first one. We'll call it A. Draw me a diastereomer of it. What would be a diastereomer of that? That's your clue. So A and B are enantiomers. Remember what an enantiomer is. Bless you. Okay, so this one's going to be C. So if I'm going to make this a diastereomer, wow. What do I got to do? I got to have the bromine and the chlorine on the opposite sides. Now, if you swapped the bottom one, that's okay. It's still in a diastereomer. So A and C are diastereomers. So do you see the difference between an enantiomer and a diastereomer? Yes? No? Maybe so? Okay, now we're going to draw all of the diastereomers for 3,4-dibromohexane using Fischer projections, and we're going to indicate pairs of enantiomers and diastereomers. Okay, so how would you, this would be like how it would be written on a test. Okay, so I want to ask you, what do you think you should do first? Yeah, just row it. Okay, so we've got 1, 2, 3, 4, 5, 6. Okay, what should you do next? That writing is thick. Make it skinny. Skinny and purple. Okay, what should you do next? Find the, yeah. Right? Okay, so if we go like this, okay, the two chiral centers are next to each other, just like they are up there. Okay, here's the top one. What's on this one? What do I put on these 3 spots? Mm-hmm. Okay, what do I put on the next one? And a. So we drew 1. Now we're going to draw the mirror image. Ooh. I'm kind of drawing them big, aren't I? That happens. Okay, now what are you going to do? See, this is me and Jackie. We're kind of falling over like that, too. We haven't had enough ethanol.
I think more ethanol makes you fall over more.
How are we doing?
The bromines on the same side.
Okay, and do what now? Put the bromines on the same side. Okay. All right, I'm going to try to write smaller because I'm having a hard time here. Okay. What?
I still got him from the mouth now.
One. Okay, how are we doing on enantiomers and diastereomers? How are you doing on those? Okay, you can do the ABCD thing if you want. Getting hang on first. Build this model. Man, these things are tight. I just picked the wrong kid, I guess. think they'd be used like a billion times over the years. Okay. All right, so I just put one carbon, but you can pretend there's two, right? All right, mirror images, right? Watch what happens when I superimpose that. Wait a minute, they all match up. Do I have chiral centers? But everything matched up, okay? This compound is special because it has two chiral centers, and what do we have through here? This is why we draw them this way. Do you see that there's a plane of symmetry through there? Yeah, right like this. All right, cutting it. Plane of symmetry, but I have chiral centers. If this compound is special, it is called a meso compound. Another term for you. There's a lot of terms in this one. Okay, it's a meso compound. Meso compounds have chiral centers and planes of symmetry. Okay, so wait a minute. Now, does it have an enantiomer? Well, what was an enantiomer?
It has its own enantiomer in it.
Yeah, but enantiomers are two separate compounds. So do I have an enantiomer? I have a mirror image, but it has to be non-superimposable, and this one is superimposable. This compound does not have an enantiomer. It's the same compound drawn twice. Okay? But wait a minute now, what about these guys? These guys are enantiomers, right? Okay, so A and B are enantiomers. What about the whole 2 to the n thing? Remember that? Where n is the number of chiral centers? Well, how many chiral centers were there? 2. What is 2 squared? 4. Do we have 4? No, we only have 3. 2 to the n is the maximum number you can have. It doesn't mean you have to have that number. It's the maximum number. Okay? So you can't have more than 4, but you might not have 4. Because if you have a meso compound, that changes things up. Okay, so how does A relate to C? How are they related? A and C. What are they? What?
Half of a rock band.
Half of a rock band, A and C?
ACDs.
You're so funny. That's funny.
That was cute. All right, A and C are diastereomers. What else is diastereomers up there?
B and C.
B and C. How do you know if you're going to have a meso compound? What are some clues? Okay, well, you have to have that plane of symmetry in you. Okay, you can cut through atoms if you have to get it. Okay, because you can have lots of chiral centers and be a meso compound. If you put a meso compound in a polarimeter, what do you think happens? Yeah, so what do you get? 0. Yeah, you get 0. Meso compounds are not optically active. Okay, remember what optically active is. All right, we didn't write down the enantiomers, so I'm going to write it down. Enantiomers are A and B. Okay, so do you see that even though there's 2 chiral centers, we only have 1 pair of enantiomers this time? I feel like I got something in my eyes. Yeah, what? Might be. I need to take it off. Okay. Any questions so far? All right, now look at the next slide. Meso compounds, you have to have 2 or more chiral centers and a plane of symmetry to be a meso compound. Okay. They do not rotate plane polarized light. They cannot have enantiomers, but they do have diastereomers. You could separate a meso compound from other things. Okay. Look for a plane of symmetry in the molecule. All right, now the next slide has molecules on it, right? Okay. Oh, you're still writing? Really? There's a lot to write? Wow. Okay. I thought I'd just leave blanks. Did I not do that?
Yeah, but the blanks always have like 2 or 3 words.
Oh my gosh.
I know it's a lot.
And then the look for the plane of symmetry and the molecule, you don't have that. That's just a big blank circle.
Oh, okay. All right, are we there now? Because we're going to do it on the next slide. All right, so I want you to tell me which of the following are meso compounds. I might have to make some of them too, so. Okay, so what are you looking for? A plane of symmetry. What do you think about that first one? I'm trying to make it. I'm making some little OHs here. Okay, is the first one a meso compound? What do you think?
Yeah.
Okay, why do you say yes? Because you had a 50-50 and you went for it?
Maybe.
Maybe?
It looks
Okay.
pretty symmetrical to me.
It looks pretty symmetrical. Okay, where's your plane of symmetry? All right, I'm going to actually put the 2 carbons for that. Okay, so there we go. Okay, so this is it, right? I got OH going back, hydrogen coming out, and down here I've got H going back and the OH coming out. Okay, look what happens if I rotate around that center. What happens? Now do you see it? That's why we draw the Fischer projections that way. It's much easier to see if there is a plane of symmetry in that molecule because everything is eclipsed. See how much harder it is to see it when it's down here? So how you doing on rotating your molecule? Got to practice. Okay, so does this one a meso compound? Yeah. Okay. Let's get us color. Meso. Okay, how about the next one? What do you think about that one? It's a ring, isn't it? Just to make it difficult, we made a ring. Because we never do it for any other reason. Okay, and hang on. So that one's there. This one's here. Okay, here it is. Okay, is there a plane of symmetry in this molecule?
Like, that's you.
I'm going to cut this CH2 right down the middle, and I'm going to cut between these 2 carbons back here. Did you see the plane of symmetry? This one is also meso. Okay, it's okay to cut atoms if you have to get your plane. Okay, how about this one? What do you think about the third one over there? He looks suspicious. He probably is. Let's see if I can make him from this one. He's got 5 carbons. That's how many I had. Okay. What are you thinking?
I'm thinking no.
You're thinking no? Okay. Here he is. Okay, that's it, right? Okay. Is there a plane symmetry? That. Okay. Do you see them? They don't have to be next to each other. They weren't next to each other over here either. Okay. The chiral centers don't have to be next to each other. Okay, how about that last one? How many chiral centers are in that last one? Too many, right? How many? 4? Should I make it?
Sure.
Thanks. Try to get all the chiral centers right. Because that's what really makes a difference, right? Okay, so I've got those 2. And then here I've got chlorine coming out and a hydrogen going back. How are you doing on your RNF? Okay, here's another carbon. Okay. Oh, there's 2 more carbons.
Oh, yeah.
I'm only putting in the hydrogens on the chiral centers, okay? I'm not putting in all those hydrogens. It's too hard to see. Okay, and you're going to have to be able to do this without necessarily having a model. Okay. All right, I almost got it. All right, let's see if I did it right. All right, so here's the 2 carbons. Then I got the chlorine coming out and the hydrogen going back. Then I got the OH going out and the hydrogen going back. And then I got the OH going back and the hydrogen coming out. And then up here I've got the chlorine going back and the H going out. What do you think? So what would be the way to figure it out? Rotate the bonds. All right, so looky here. Is there a plane of symmetry in there?
Yep.
Everybody see it right there? Okay, so you're going to have to look at them and maybe rotate them around a little. So every one of those was Meso. Do you need one that isn't Meso? Just to make you happy? Okay, what about? Is that one Meso? Okay, what was your first clue?
Added that extra delta at the end.
Yeah, because there's 2 carbons here and there's 3 there. Okay, what if I showed you this one? Is that one Meso? How are you going to decide? What do you got to do? Because now we don't have 2 different groups. Okay, all 3 groups are the same. Agree? Okay, so this one I have going like this. And this goes down here. Okay. And then that goes down. All right, so I got it like that. So what do I got to do to decide if it has a plane of symmetry? I'm going to rotate through this bond. So when I pull that hydrogen back, look what happened. Is there a plane of symmetry? No, so it's not Meso.
What do you mean there's not a
You see, there's no plane of symmetry. This is a H and this is an OH. This is an OH and this is an H. It's like taking a mirror through the center of the molecule. There's no plane of symmetry in this molecule. It doesn't matter that this has an OH and an H and this has an OH and H. They have to match when you cut it in half. Okay, you got to be the same on both sides. It's like you cut your little person, you have a hand and a hand. You have a foot and a foot. Okay, you have an eye and an eye. But we cut the nose in half. That's okay. Just like cutting a molecule in an atom in half. Okay, that's called a plane of symmetry. Okay. Okay, what is the relationship between the following compounds? Think about those now. These are your favorite questions on the test, I know. Why you're practicing. I'm up to 23. Yep, it's D. They're diastereomers.
Not even the same compound.
Oh, you're right. They're not. They're E. I fell for my own question. Okay.
I just got,
How many carbons are there?
Can we please make it Z because you fell for it too?
No. No, I'm going to learn. Man, this is tight. Okay. Look at this.
trick or treat.
I blame it on the glare from the lights, but you know.
That means we're there. Same.
Okay. This one has 5 carbons down the center. Okay. Now you're all going to watch for that on the test, right?
Probably.
Probably.
Oh, cheers.
Where did the
Nice.
Oh. That we were done.
No, we're never done with cheer. We're never done with anything. It all comes back to home.
Wow. Oh, this is funny.
I got chlorines on there. Okay, so this one is on. Okay. Put a H there. Here's our little chair. How did I do it? Good. Okay, let me do it the same way. Okay, there they are. Okay, that's the first one. All right, I got 20. 4 more people need to make a guess.
Someone go and ask you.
Yeah, it's for the
It's done.
Okay. What do you think? Okay. If you were to name this one, how would you name the first one? Because that's a way that you can figure it out.
1,2-dichloro.
Okay. Okay. What goes out here?
This.
Yeah. All right. What's this one? Uh-huh. Okay. So what are they?
Oh, what?
Yeah.
Well, I mean, I got it right. But
Okay. But you got it right for a different reason.
yeah,
That's
because
okay.
I guessed.
I
thought
because they were facing different, right, at least one.
Okay. So basically why it's not E. Okay. If it was E, this would have to be up and axial, and that would have to be up and equatorial. Yeah. Okay. Okay, now I'm going to ask you another question on it. Tell me if the two chiral centers are R or S.
Okay, good.
Okay, it's not a clicker question, it's just a question. Okay, so here's the molecule, I made it. So how do you do it if there's more than one chiral center? You do one and then you do the other one, okay? All right, so let's do the back one first. Here's the back one, okay? So what can you tell me about those groups? Chlorine, hydrogen, the ring, and the ring. Chlorine is what? 1. All right, what's the hydrogen? 4. Let's get the easy part out of the way. Okay, now how do you decide where 2 and 3 are? You're going to go around the ring until you get to the first point of difference. What's going to be that? So I got C and C, right? That's the same. Then what? I will have C, H, and H up here for this carbon. What about this carbon here? I will have Cl, C, and H. So what am I going to compare? Right, which is going to be the chlorine and I guess a hydrogen because the carbons are the same, but it doesn't matter. The chlorine wins, right? So which part of the ring is number 2? The bottom part. And which part is number 3? There. Now, can you tell me if you think it's R or S? Okay. So let me get it in the same orientation. Okay. Okay, here it is. Okay, I'm going to grab number 4 and pull it away. And we go 1, 2, 3. What is that? R. Did you get it? Okay, what's the bottom one? Okay, I'm going to erase this deal, the name, because it's in the way. Because I think it'll. You want to be the eraser?
No, it's tiny.
I made it tiny because I was trying to avoid killing that poor hydrogen I drew in. All right, so, because see, I can pick. What can I say? All right, so who is 1? All right, who is 4? All right. Okay, now we got to decide the ring up there. Okay, so what's going to be 2 and what's going to be 3? Right. And then this side of the ring is 3. Okay, so we've got, hang on, let me get it right. All right. So there's those 2. And then here's the green. And here's the red. Okay. All right. So which one do I grab? The white one. And I pull it this way. And what do I get? Yes. How'd it go? Okay. Any questions? When you do a ring, you just go to the first point of difference. It's okay that they're holding hands back here. It's okay. So, but then you still orient the same way once you've decided. These guys are connected. They're part of the ring. But you still grab number 4 and pull it away and do your 1, 2, 3. Okay? Okay. Resolution. In this day and age, there's all kinds of resolutions. Okay, resolution is the separation of 2 enantiomers. It can be pretty difficult to do. Louis Pasteur did the first one in 1848. He got lucky. Must be nice, huh? Okay, he separated plus and minus tartaric acid using a microscope and tweezers. He was looking at his crystals. Do you ever look at your crystals in lab because they're cool? No? You should look at your crystals. Okay? Have you ever noticed when you put it in the mel temp and it magnifies it? That, I guess it's a digimel now. But it still magnifies it so you can really see them, and sometimes they look cool. Yeah. Look at your crystals. That's the moral of the story. Okay. So he was looking at his crystals and he noticed that some of the crystals were mirror image of others. And he thought, I wonder why that is. And he actually separated them truly with a microscope and tweezers. That's what he says. These are the tartaric acids. This one is 2R3R and this is 2S3S. Okay. This one, when you put it in a polarimeter, it was dextrorotatory. So that means it rotated the light clockwise. Levorotatory rotates the light counterclockwise. Okay? Okay, it's okay. You don't have to know what tartaric acid is, but anyway, that was what he did. Okay, so how do we do it now? Well, remember, sometimes one enantiomer can cause birth defects and the other one maybe wouldn't. So what we do is we have to separate them. In order to figure that out, you have to look at each enantiomer separately. So if you don't have a way to make it that where you only get one enantiomer, you have to separate them later on. Remember that enantiomers have the same physical properties. Okay, so let's say you have a mixture of enantiomers. One is dextrorotatory, one is levorotatory. Doesn't matter what they are, okay? But you want to separate them. So one thing you can do is add a single enantiomer that will react with them. So that's what this is. It's referred to as a resolving agent. They are typically isolated from nature, okay? A lot of them are real poisonous too. And so we won't be doing this in lab. I don't even think Jay-Z would have you do. Okay, but they're poisonous and they're real expensive because they're isolated from natural sources, and that can be really difficult. So you're going to react it with them, and you're going to make, you see how here I've got plus, plus, and I've got minus, plus. Now what I made are diastereomers. Diastereomers have different physical properties. Okay, they have different. Now I can separate them. How easy or hard it is depends on just what they are. Okay, but theoretically you can separate them. So now you've got these two things, the plus plus and the minus plus, okay? And they are in separate Erlenmeyer class. Okay, you do something else to get the thing you added, the P plus, off. Okay, and now you have them separated. Don't get them mixed up. Keep them well labeled. Does that make sense? Then you can hopefully reuse P plus because it's expensive, and you can use it to do another one. Okay, that is the end of the chapter. Okay, we will start chapter 6 on Friday. All right, it says, how many stereoisomers can you draw for the molecule below? So I want you to see if you can come up with how many. Okay, and I'll talk about that at the very beginning. All right, y'all have a good Halloween Reformation Day. Yay for Martin Luther.
Mine probably is not too good. Like I simply can't. I live in the dorm, so I'm not really getting candy, but if I go to someone else's house, I'll take it.